March 17, 1942, Bandung Airfield, Java. The Boeing B-17E Flying Fortress sat motionless on the tarmac, its forward fuselage section torn open by the crash landing that had ended its final mission 3 days earlier. Japanese Army engineers approached the wreckage with particular interest, not in the airframe or engines that their colleagues were already documenting, but in a device mounted in the nose section, a cylindrical apparatus roughly 2 feet tall, constructed from precisely machined brass and aluminum components, connected to an elaborate system of gears, gyroscopes, and optical elements. This was the Norden Mark 15 bombsight, serial number 47238, the most closely guarded secret in American military aviation. Within hours, this single device would be carefully extracted from the wreckage and shipped to Tokyo for examination by Japan's most accomplished engineers and scientists. What they would discover upon disassembling it would fundamentally challenge their understanding of American technological sophistication and manufacturing capability. The bombsight represented not just advanced engineering, but an entire industrial philosophy that Japan had not achieved. Over the following months, Japanese technical teams would document every component, measure every tolerance, and attempt to understand the principles that made this machine function. The conclusions they reached would prove devastating to Japanese confidence in their ability to match American precision manufacturing. The discovery of intact Norden bombsights in the Dutch East Indies came as Japanese forces completed their conquest of the resource-rich islands. At multiple airfields across Java, engineers found damaged American B-17 bombers that had been abandoned during the hasty Allied withdrawal. While airframes could be studied and engines examined, the Norden bombsights represented something entirely different. These devices embodied precision engineering at a level Japan had never attempted in any military application. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Lieutenant Commander Tsuyoshi Nishizawa of the Imperial Japanese Navy's Technical Research Division supervised the initial recovery of Norden bombsights from captured aircraft. A graduate of Tokyo Imperial University with advanced training in precision instruments, Nishizawa understood immediately that these devices represented engineering capabilities that exceeded anything in Japanese military arsenals. The bombsight from the Bandung B-17, though damaged in the crash, remained largely intact, with its critical components still assembled. 2 additional Norden bombsights were recovered from B-17 bombers at Surabaya and Malang airfields, providing multiple examples for detailed study. The devices were packed with extraordinary care and shipped aboard the aircraft carrier Akagi to Yokosuka Naval Arsenal near Tokyo. There, Japan's most advanced technical research facility, the Kaigun Gijutsu Kenkyujo, or Naval Technical Research Institute, prepared to conduct the most comprehensive examination of enemy equipment Japanese engineers had yet attempted. The institute employed Japan's finest mechanical engineers, optical specialists, and precision instrument makers. These men had designed fire control systems for battleships, torpedo calculators for submarines, and gun sights for fighter aircraft. They represented the pinnacle of Japanese technical capability. When the Norden bombsights arrived at Yokosuka in April 1942, these experts began an examination that would continue for more than 2 years and fundamentally reshape Japanese understanding of American industrial capacity. The Norden bombsight had been developed beginning in 1928 by Carl Norden, a Dutch immigrant engineer working in New York. The United States Navy provided funding through a series of contracts, seeking a device that could enable accurate bombing from high altitude. By 1941, the Mark 15 variant had become standard equipment in all American heavy bombers deployed to combat theaters. The device combined an analog computer, gyro-stabilized platform, optical sighting mechanism, and automatic flight control interface. It could calculate the trajectory of bombs dropped from altitudes exceeding 20,000 feet, accounting for aircraft speed, altitude, wind drift, and ballistic characteristics of different bomb types. When properly calibrated and operated, the Norden could place bombs within a 100-foot radius from altitudes of 20,000 feet under ideal conditions. This represented accuracy impossible to achieve with any other bombing method then in use. The security surrounding the Norden Bombsight had been extraordinary even by wartime standards. Bombardiers were required to swear oaths of secrecy. The devices were stored in guarded vaults when not in use. Bombardiers received explicit orders to destroy their bombsights if capture appeared imminent, using thermite grenades specifically designed for this purpose. Despite these precautions, the chaos of the Japanese advance through the Dutch East Indies in early 1942 had resulted in at least 6 Norden bombsights falling into Japanese hands before they could be destroyed. Japanese engineers at Yokosuka began their examination with photographic documentation. Every angle of the assembled bombsight was photographed in detail. External dimensions were measured precisely. Mounting interfaces were documented. Control inputs were identified and their functions noted. The optical system received particular attention from specialists who examined the telescope's construction and documented the precision grinding of its lenses. Only after this comprehensive, external documentation did engineers begin the delicate process of disassembly. The disassembly proceeded slowly, with each component carefully removed, photographed, measured, and catalogued before the next was touched. What engineers discovered as they worked deeper into the mechanism challenged every assumption they held about American manufacturing capability. The Norden bombsight contained approximately 2,000 individual components. Every part was manufactured to tolerances measured in 10,000ths of an inch. Gears showed tooth profiles ground to mirror finishes with spacing variations under 2 10,000ths of an inch. Bearing surfaces were polished to optical quality, so smooth they appeared almost liquid under magnification. Gyroscope rotors were balanced to tolerances that eliminated vibration even at rotational speeds exceeding 10,000 revolutions per minute. The precision required to manufacture such components exceeded anything Japanese instrument makers had achieved in production devices. Japanese military equipment certainly contained precision components. Torpedo guidance systems, naval fire control computers, and aircraft gun sights all required careful manufacturing. But these devices were essentially hand-built by master craftsmen, with components individually fitted and adjusted to achieve required performance. Each device was unique, requiring skilled technicians for maintenance and repair. The Norden bombsight appeared fundamentally different. Evidence suggested that its components were not individually crafted, but mass-produced to specifications so precise that any part would function correctly in any bombsight of the same model without adjustment. This implied manufacturing capability that Japanese industry had never demonstrated. The optical system particularly impressed Japanese specialists. The telescope used multiple lens elements, each ground and polished to precise focal lengths, and then coated with anti-reflection treatments. The lens coatings, a recent innovation in optical engineering, reduced light loss and improved image clarity under difficult conditions. Japanese optical manufacturers understood lens coating in theory, but had not successfully implemented it in production equipment. The Norden's lenses showed coating quality that appeared completely uniform across the entire optical surface, suggesting automated coating processes rather than manual application. The telescope mounting incorporated a complex gimbal system that isolated the optical path from aircraft vibration and movement. This system used precision bearings manufactured to tolerances that eliminated any detectable play in the mounting. Japanese gun sights and telescopes used bearings that required periodic adjustment as wear developed. The Norden's bearings showed no evidence of wear-related adjustment mechanisms, suggesting they were designed to maintain their precision throughout the device's service life. The analog computer, at the heart of the bombsight, presented even greater challenges to Japanese understanding. This mechanism consisted of dozens of precisely machined gears, cams, and linkages that performed continuous calculations of bombing trajectory. Operators input current aircraft altitude, airspeed, and wind conditions through calibrated dials. The mechanical computer then calculated the precise moment when bombs should be released to hit the designated target, automatically accounting for the ballistic characteristics of different bomb types. Japanese engineers examining this mechanism found themselves confronting mechanical computing sophistication they had not imagined possible. The gear trains used helical cut gears rather than straight cut designs, distributing loads across multiple teeth and allowing smoother operation with less backlash. The precision of the gear cutting suggested automated machinery capable of holding tolerances across hundreds of teeth on gears ranging from thumbnail size to several inches in diameter. Each gear appeared identical to corresponding gears in other Norden bombsights examined, confirming that these were not individually crafted components, but standardized parts produced through systematic manufacturing processes. The cams that translated rotational input into specific output values were machined to profiles that showed no detectable deviation from theoretical curves. Japanese cam grinding typically involved skilled machinists who gradually refined profiles through trial and error until desired performance was achieved. The Norden's cams appeared to have been ground on automated equipment that precisely reproduced mathematical profiles without human intervention. The ball bearings throughout the mechanism presented another revelation. These were precision ground spheres, each one identical in diameter to within 1/10,000th of an inch. Japanese ball bearing manufacture involved considerable hand sorting to match bearing sizes for precision applications. The Norden contained hundreds of precision ball bearings that appeared to require no sorting, suggesting manufacturing processes that produced uniform products without individual inspection and matching. The gyroscopes that stabilized the bombsight platform demonstrated engineering sophistication that particularly troubled Japanese specialists. Each gyroscope consisted of a precisely balanced rotor spinning in a housing that minimized friction through the use of precision bearings and careful lubrication. The rotor balance was so precise that the gyroscopes could maintain stable operation for hours without deviation, providing the steady reference platform necessary for accurate bomb trajectory calculations. Japanese gyroscopes for torpedo guidance and shipboard stabilization were carefully crafted devices, each one individually balanced and adjusted by specialist technicians. They required regular maintenance and periodic rebalancing to maintain performance. The Norden's gyroscopes showed no evidence of adjustment mechanisms beyond basic calibration inputs, suggesting they were manufactured to such precise specifications that no individual tuning was necessary. By summer of 1942, Japanese engineers at Yokosuka had completely disassembled all three captured Norden bombsights and documented every component in exhaustive detail. Technical drawings filled hundreds of pages. Photographs captured every angle and aspect. Measurements recorded dimensions and tolerances throughout. Metallurgical analysis identified alloys and heat treatments. Optical specialists documented lens curvatures and coating characteristics. The accumulation of data painted a disturbing picture of American technological capability. Commander Nishizawa prepared a comprehensive report for submission to Navy Technical Headquarters in Tokyo. The document, classified at the highest secrecy level, contained observations that would prove profoundly troubling to Japanese military leadership. The report's technical findings documented precision manufacturing at scales Japan had never achieved. American factories were producing complex precision instruments containing thousands of precisely manufactured components as standard production items, not as individually crafted specialty equipment. The tolerance standards maintained throughout the Norden bombsight exceeded Japanese capabilities in multiple technical areas simultaneously. Gear cutting, bearing manufacture, optical grinding, metal forming, and surface finishing all demonstrated systematic precision that Japanese industry could not match. The report noted that attempting to reverse engineer the Norden bombsight would require not just copying the design, but developing entirely new manufacturing processes and quality control systems. Japan lacked the machine tools necessary to produce components to the required tolerances. More fundamentally, Japan lacked the industrial infrastructure to produce such machine tools. The technical gap represented not months or even years of development, but a fundamental disparity in industrial maturity that could not be quickly overcome. Most disturbing to Japanese military planners was the report's conclusion regarding American industrial depth. The Norden Bombsight represented military equipment produced in quantities of thousands per year. If American factories could manufacture precision instruments at this sophistication level as routine production items, their industrial capability exceeded Japanese estimates by factors of magnitude. Every American heavy bomber carried one Norden Bombsight. The United States was producing thousands of heavy bombers per year. This meant American factories were manufacturing thousands of Norden bombsights annually, each containing 2,000 precision components manufactured to tolerances Japanese industry could not consistently achieve, even in laboratory conditions. The implications extended far beyond bombing accuracy. An industrial base capable of such precision manufacturing at such production scales could produce any military equipment to specifications that would exceed Japanese capabilities. Artillery fire control systems, naval gun directors, radar equipment, radio communications systems, all would benefit from the same precision manufacturing capability that produced the Norden Bombsight. Japan had entered a war against an opponent whose industrial sophistication exceeded Japanese understanding. Japanese efforts to develop an equivalent bombsight began almost immediately after the initial Yokosuka examination. The Navy Technical Bureau assigned the project highest priority, allocating resources and personnel to develop a Japanese precision bombsight, incorporating the principles observed in the Norden. The project quickly encountered fundamental obstacles that confirmed the Yokosuka report's pessimistic conclusions. Japanese machine tool. Manufacturers could not produce equipment capable of maintaining the tolerances required. Gear-cutting machines available to Japanese industry could not consistently hold dimensions within 2/10,000ths of an inch across hundreds of gear teeth. Bearing manufacturers could not produce balls uniform enough to eliminate sorting and selection. Optical manufacturers could not apply coating evenly enough to match Norden lens performance. Each technical challenge revealed deeper problems in Japan's industrial infrastructure. The machine tools needed to manufacture precision bombsight components required precision machine tools to manufacture them. Those machine tools, in turn, required even more sophisticated equipment for their manufacture. Japan lacked multiple levels of this manufacturing infrastructure that American industry had developed over decades of civilian and military production. The development program struggled through 1942 and into 1943, making incremental progress but never approaching the performance or reliability of the captured Norden bombsights. Prototype Japanese bombsights functioned under ideal conditions but proved too delicate for service use. Components required individual fitting and adjustment. Maintenance demanded specialist attention. Production costs exceeded anything acceptable for mass production. By mid-1943, Japanese engineers privately acknowledged that their bombsight development program had failed to produce a device comparable to the Norden. The technical gap was simply too large to bridge during wartime conditions with available resources and infrastructure. This failure had devastating implications for Japanese strategic bombing capability, though Japan's desperate situation by 1943 meant strategic bombing had become largely irrelevant to Japanese military operations. The examination of captured Norden bombsights had revealed truths that extended far beyond the immediate question of bombing accuracy. American industry possessed manufacturing sophistication that Japan could not match. American precision manufacturing operated at scales that transformed what should have been specialty equipment into mass production items. American industrial depth suggested that any direct comparison of weapon capabilities understated the true disparity between Japanese and American military potential. These realizations emerged gradually through 1942 and 1943, as Japanese engineers accumulated more evidence from additional captured American equipment. Each examination reinforced the same disturbing conclusions. American weapons were not simply numerous, they were manufactured to standards that Japanese industry could not achieve. The precision was not concentrated in a few showcase systems, but pervaded all American military equipment, from bomb sights to artillery fuses to aircraft instruments. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Norden Bombsight examination had a particularly significant impact because it revealed American precision manufacturing in a device whose sophistication could not be denied or rationalized away. This was not a question of different design philosophies or tactical doctrines. This was direct evidence of superior manufacturing capability expressed in thousands of precisely machined components that Japanese industry simply could not reproduce. The strategic implications of the Norden Bombsight examination became clearer as the Pacific War progressed through 1943 and into 1944. American bombing accuracy improved steadily as bombardier training incorporated lessons from combat experience and as newer variants of the Norden entered service with enhanced capabilities. Japanese air defenses, meanwhile, degraded under relentless attrition as pilot losses mounted and aircraft production failed to keep pace with combat losses. By late 1943, American B-24 Liberators and B-25 Mitchells were conducting precision strikes against Japanese shipping, naval facilities, and industrial targets throughout the Pacific. The accuracy of these attacks, guided by Norden bombsights, exceeded anything Japanese forces could achieve with their own bombing equipment. Japanese bombers relied on visual aiming techniques that required low-altitude approaches, exposing aircraft to intense anti-aircraft fire and reducing survival rates dramatically. The technical examination at Yokosuka had documented not just the Norden's construction, but its operational principles. Engineers understood how the device calculated bombing trajectories, how it interfaced with the aircraft's autopilot to guide the bomber onto the precise course needed for accurate bomb release, and how bombardiers used the optical sight to align the target and initiate the bombing sequence. This knowledge proved useless without the manufacturing capability to produce equivalent devices. Understanding principles did not bridge the industrial gap. Japanese naval air units operating in the South Pacific through 1943 reported increasing difficulty in achieving effective bombing results against American naval forces. American fighters, guided by radar and coordinated through sophisticated radio communications, intercepted Japanese bombing formations before they could reach their targets. When Japanese aircraft did manage to approach American ships, anti-aircraft fire of unprecedented intensity and accuracy, directed by radar-controlled fire control systems, destroyed aircraft at devastating rates. The few Japanese bombers that survived to release their weapons discovered that American ships maneuvered with such speed and precision that bombing accuracy at altitude became virtually impossible without the kind of automated bombsight that only American forces possessed. Japanese pilots resorted increasingly to low-level attacks and eventually to suicide tactics as the only methods offering reasonable probability of hitting maneuvering targets. The contrast between American and Japanese bombing capabilities became most apparent in the strategic bombing campaign against Japan itself, which began in earnest in 1944. When Boeing B-29 Superfortresses commenced operations from the Mariana Islands in November 1944, they carried the Norden Mark 15 bombsight as standard equipment, the same device Japanese engineers had examined so carefully at Yokosuka more than 2 years earlier. The B-29 raids initially attempted precision bombing of Japanese industrial targets from altitudes above 30,000 feet, where Japanese fighters and anti-aircraft fire proved largely ineffective. The Norden bombsights enabled bombardiers to aim at specific factory, buildings, power plants, and transportation nodes from altitudes where visual identification of such targets would normally be impossible. Weather over Japan and mechanical difficulties with the B-29's complex systems limited the effectiveness of these early high-altitude precision raids, but the capability itself demonstrated the vast gulf between American and Japanese bombing technology. Major Saburo Endo of the Imperial Japanese Army Air Force Technical Staff had been among the engineers who examined the captured Norden bombsights at Yokosuka in 1942. By 1944, he served with air defense units near Tokyo, coordinating fighter responses to B-29 raids. In letters preserved after the war, Endo wrote candidly about the psychological impact of facing weapons systems Japan could neither duplicate nor effectively counter. We understood from our examination of the captured bombsight that American industry could produce precision instruments we 6. could not match, Endo wrote. But understanding this in theory is different from witnessing formations of enemy bombers operating at altitudes our fighters cannot effectively reach, dropping bombs with accuracy our own bombers could never achieve, guided by devices we examined but could not reproduce. The enemy's industrial superiority is not merely a matter of numbers but of fundamental technological capability. The examination of captured American equipment, including the Norden Bombsight, had revealed to thoughtful Japanese engineers by mid-war that defeat was inevitable. American industrial capacity was not just larger than Japan's, it was qualitatively different, capable of producing advanced technology as routine manufacturing, rather than as specialized handcrafted equipment. This industrial maturity, developed over decades of civilian manufacturing experience, could not be matched by any effort Japan could make during wartime. Japanese industry in 1944 was desperately trying to maintain production of existing weapon types, while American industry was routinely introducing improved versions of weapons that already exceeded Japanese capabilities. The gap was widening, not closing. Every month of continued war saw American advantages grow, while Japanese capabilities degraded under material shortages, bombing damage, and loss of skilled workers to military conscription. The failure of Japan's bombsight development program represented in microcosm the broader failure of Japanese industrial mobilization. Japan could not simultaneously fight a war and develop the industrial infrastructure needed to match American manufacturing sophistication. The machine tools, quality control systems, and manufacturing processes required for precision mass production took years to develop and implement. Japan had entered the war, hoping that tactical skill and fighting spirit could overcome material disadvantages. By 1944, it was clear this hope had been an illusion. The strategic bombing campaign against Japan intensified through 1945 as American forces captured Iwo Jima and Okinawa, providing bases closer to the Japanese home islands. B-29 raids shifted from high-altitude precision bombing to low-altitude area incendiary attacks that devastated Japanese cities. The change in tactics reflected recognition that weather conditions over Japan made precision bombing unreliable, but the capability for precision attack remained available when conditions permitted. On the night of March 9th to 10th, 1945, more than 300 B-29s conducted a low-altitude incendiary raid against Tokyo that created a firestorm, killing an estimated 100,000 civilians and destroying 16 square miles of the city. The raid demonstrated American willingness to employ area bombing when precision attacks proved insufficient, but also demonstrated the vast scale of American bombing capability. 300 heavy bombers in a single raid represented more aircraft than Japan could assemble for any operation by that stage of the war. Japanese technical personnel who had examined the Norden Bombsight in 1942 watched these raids from the ground, understanding that each B-29 carried the same precision bombsight they had studied so carefully. The device had revealed American industrial capabilities that seemed almost incomprehensible at the time. 3 years later, those capabilities had been fully demonstrated through military operations that Japanese forces could neither prevent nor effectively oppose. The industrial disparity extended to every aspect of military technology by war's end. American proximity fuses for anti-aircraft shells, incorporating miniature vacuum tubes and sophisticated electronic circuits, demonstrated electronics manufacturing capability Japan had never approached. American radar systems, mass-produced and installed throughout American forces, provided detection and fire control advantages that Japanese forces could not counter. American radio communications equipment, standardized and produced in quantities that equipped every level of American forces, enabled coordination and control that Japanese forces attempted through more primitive means. Each examination of captured American equipment told the same story. American industry possessed manufacturing sophistication that transformed theoretical technology into practical weapons systems at scales that overwhelmed Japanese forces through sheer quantity of capable equipment. The Norden Bombsight had been one of the first captured devices to reveal this reality so clearly that Japanese engineers could not rationalize or dismiss the evidence. After Japan's surrender in August 1945, American technical intelligence teams surveyed Japanese military research facilities and industrial plants. The reports documented Japanese efforts to develop precision bombing equipment, radar systems, and advanced weapons that might have narrowed the technological gap. In every case, the reports noted the same fundamental limitation. Japanese industry lacked the manufacturing infrastructure to produce advanced technology at scales that would affect military outcomes. The Yokosuka Naval Technical Research Institute, where captured Norden bombsights had been examined in 1942, was surveyed by American teams in September 1945. The facility's laboratories contained Japanese bombsight prototypes that engineers had been developing throughout the war. American technical experts examined these devices and documented their characteristics. The Japanese bombsights incorporated clever design features and showed sophisticated engineering. They also showed clear evidence of manufacturing limitations that prevented them from matching Norden performance or reliability. Components were hand-fitted rather than precision, manufactured to interchangeable standards. Tolerances were looser than American equivalents. Materials were less suitable, reflecting shortages that had forced substitutions. Assembly required skilled technicians rather than semi-skilled workers following systematic procedures. The devices functioned adequately under ideal conditions, but proved too delicate for routine service use. Everything about these Japanese bombsights reflected an industrial base that understood advanced technology in theory, but could not manufacture it effectively at scale. The American technical teams documented Japanese manufacturing methods throughout surveyed facilities. They observed skilled craftsmen performing operations that American factories accomplished with automated machinery. They documented hand operations where American industry used precision tooling. They noted individual fitting and adjustment where American manufacturing employed interchangeable parts. The cumulative evidence confirmed what the examination of American equipment had shown Japanese engineers during the war. The industrial gap was not merely a matter of scale, but of fundamental manufacturing philosophy. American industry had been organized around systematic mass production for decades before the war. Automobile manufacturing, electrical appliance production, and consumer goods manufacture had driven development of precision mass production techniques that could be readily applied to military equipment. Workers in American factories possessed skills developed through years of civilian manufacturing experience. Machine tool manufacturers had refined equipment over decades of continuous improvement. Quality control systems had evolved through competitive commercial markets that rewarded consistency and reliability. Japan had industrialized rapidly, beginning in the Meiji era of the late 19th century. But this industrialization had emphasized heavy industry and basic manufacturing rather than the precision mass production that characterized American consumer goods industries. Japanese manufacturing excellence existed in traditional crafts and in heavy industrial products like ships and steel. But precision mechanical manufacturing at mass production scales had not developed to the same extent. The war had exposed this gap brutally. The post-war occupation of Japan brought American manufacturing advisors who worked with Japanese industry to implement modern production methods. The experience of examining captured American equipment during the war had prepared Japanese engineers to understand what these advisors were teaching. They had seen in the Norden bombsight and other captured devices what systematic precision manufacturing could achieve. They had attempted to replicate it during wartime and failed due to lack of infrastructure and time. In peacetime, with American assistance and access to American machine tools and manufacturing technology, Japanese industry could finally implement the production methods they had glimpsed in captured equipment. The transformation took more than a decade. Japanese factories rebuilt after wartime destruction incorporated American manufacturing principles from the start. Machine tool manufacturers began producing precision equipment to standards that had been impossible during the war. Quality control systems, based on statistical methods, replaced traditional reliance on skilled craftsmanship for ensuring product quality. Workers learned to operate precision equipment rather than performing hand operations. The manufacturing culture gradually shifted from valuing individual craftsmanship to valuing systematic processes that enabled consistent results at scale. By the early 1960s, Japanese manufacturing had achieved precision mass production capability comparable to American industry. Companies like Toyota, Sony, and Canon demonstrated that Japanese factories could produce products requiring precision manufacturing in quantities and at quality levels matching or exceeding American products. The industries that emerged included precision optical equipment, electronics requiring precise component manufacturing, and automotive products demanding reliable mass production of thousands of components. The engineers who had examined the Norden Bombsight at Yokosuka in 1942 and subsequently worked in post-war Japanese industry explicitly credited that examination with teaching them principles that guided post-war reconstruction. In technical society, presentations and engineering journal articles through the 1950s and 60s, these engineers described how studying American equipment during wartime had revealed manufacturing philosophies that Japanese industry needed to adopt. The Norden Bombsight became a case study in Japanese engineering education, used to illustrate how systematic examination of advanced technology can reveal principles beyond the immediate device being studied. Engineering students learn to look past surface features to understand underlying manufacturing systems. They learned that matching advanced technology requires not just copying designs, but implementing the production systems that enable such technology to be manufactured reliably at scale. Professor Hiroshi Nakamura, who had been a junior engineer at Yokosuka during the Norden examination and later became a prominent manufacturing engineering educator at Tokyo University, wrote extensively about the lessons learned from examining captured equipment. The Norden Bombsight taught us that modern manufacturing is not about skilled hands, but about systematic processes, Nakamura wrote in a 1968 textbook that became standard in Japanese engineering programs. We could measure every dimension and document every component, but we could not reproduce the device because we lacked the manufacturing systems that made such precision routine rather than exceptional. That lesson guided Japan's post-war industrial development. The story resonated in Japanese business culture through the decades of rapid post-war growth. The examination of the Norden Bombsight represented a moment when Japanese engineers had to confront their limitations honestly, without the propaganda and wishful thinking that had characterized much wartime thinking. They had held American technology in their hands, measured it precisely, and understood definitively that they could not match it with existing capabilities. This honest assessment, painful at the time, became the foundation for genuine improvement. Japanese companies developing precision manufacturing in the 1960s and 70s often referenced the wartime examination of American equipment as a cautionary tale against overconfidence and a model for honest technical assessment. When Canon developed advanced camera optics in the 1960s, engineers explicitly studied the lens grinding and coating techniques that had impressed Japanese optical specialists examining Norden bombsights 20 years earlier. When Toyota developed precision transmission components for mass-produced automobiles in the 1970s, engineers referenced the herringbone gear cutting that Japanese engineers had documented in captured American equipment but couldn't reproduce during wartime. The transformation of Japanese manufacturing from craft-based production to systematic mass production represents one of the most significant industrial developments of the 20th century. Japan evolved from a nation whose wartime industry could not match American precision manufacturing to a nation whose post-war industry set new standards for manufacturing quality and efficiency. The seeds of this transformation were planted during the war when Japanese engineers examined captured American equipment and learned lessons they would apply in peacetime reconstruction. The Norden bombsight itself became obsolete relatively quickly after World War II. Jet aircraft operating at higher speeds made the device's mechanical computing inadequate for accurate bombing. Radar bombing systems and eventually laser-guided weapons replaced optical bombsights for precision attack missions. By the 1950s, the Norden had been retired from American military service, its secrets no longer worth protecting. But the industrial principles embodied in the Norden bombsight remained relevant. Precision mass production, systematic quality control, interchangeable parts manufacture, and automation of skilled operations continued to define advanced manufacturing long after the specific device that demonstrated these principles had become a museum piece. The lessons Japanese engineers learned from examining the Norden in 1942 influenced Japanese industrial development for decades and contributed to manufacturing advances that benefited industries worldwide. In manufacturing engineering today, the story of Japanese engineers examining the Norden Bombsight serves as a case study in technology transfer and industrial development. It demonstrates that understanding advanced technology requires looking beyond the device itself to comprehend the manufacturing systems that produced it. It shows that matching competitors' capabilities requires not just copying their products, but implementing equivalent production systems. It illustrates that industrial maturity develops over time through accumulated experience and cannot be rapidly created even with accurate knowledge of advanced designs. The story also serves as a reminder that industrial capability ultimately determines military outcomes in modern warfare. Japan entered World War II with tactical advantages, trained personnel, and sophisticated strategy. These advantages proved insufficient against an opponent whose industrial base could produce advanced weapons in overwhelming quantities. The examination of the Norden Bombsight revealed this reality to Japanese engineers years before final defeat, though political and military leadership continued the war long after. Thoughtful technical personnel understood that industrial disparity made ultimate victory impossible. The Carl Norden Company, which manufactured the bombsight, produced approximately 50,000 units during World War II, equipping not only American forces but Allied bombers operating in every theater. Each bombsight contained 2,000 precision components manufactured to tolerances. Japanese industry had examined carefully but could not match. The scale of this production, 50,000 complex precision instruments manufactured during a 4-year period, demonstrated industrial capacity that exceeded anything Japan could achieve even in peacetime under ideal conditions. Japanese engineers who examined captured Norden bombsights in 1942 understood this at the time. They wrote reports stating clearly that American industry capability exceeded Japanese capacity by factors that could not be overcome during wartime. These reports, classified and restricted to senior technical and military officials, had little impact on strategic decisions, but the engineers who wrote them carried that knowledge forward into post-war careers, where it influenced industrial development policies that transformed Japan from defeated nation to industrial leader. The examination of the Norden bombsight at Yokosuka Naval Technical Research Institute in 1942 represents a pivotal moment when Japanese technical experts confronted evidence of American industrial superiority so clear that denial became impossible. The device sat on laboratory benches in Tokyo, its components carefully arranged and measured, its sophistication documented in hundreds of pages of technical drawings and photographs. Every measurement confirmed what Japanese engineers had feared. American industry possessed capabilities Japan could not match. That realization, painful and devastating during wartime, became transformative during post-war reconstruction. Japanese industry rebuilt itself consciously implementing the manufacturing principles that captured American equipment had revealed. The engineers who had measured tolerances in Norden bombsight gears became the architects of Japanese precision manufacturing industries. The optical specialists who had studied Norden lens coatings became leaders in Japanese camera and electronics industries. The technical knowledge gained from examining enemy equipment during wartime became the foundation for industrial capabilities that made Japan a global manufacturing leader in peacetime. The Boeing B-17 Flying Fortress that carried Norden bombsight serial number 47238 to Java in early 1942 was destroyed in the crash landing that ended its mission. The aircraft became scrap metal salvaged by Japanese forces for its aluminum content. Bombsight survived, was carefully preserved, and taught lessons that influenced industrial development for decades. In the final accounting, that single precision instrument may have had greater long-term impact through the industrial lessons it taught than through any bombs it guided to targets during its brief operational service. The story that began on March 17, 1942, with Japanese engineers approaching a damaged B-17 on a Java airfield, ended decades later with Japan and America as partners in advancing manufacturing technology. The examination of that captured bomb site had taught Japanese engineers that their industry could not match American manufacturing sophistication during wartime. More importantly, it taught them why, and in understanding why, they learned how to ensure that industrial inadequacy would never again limit Japan's capabilities. The Norden Bombsight served as teacher to its enemies, and they learned the lesson thoroughly enough to transform defeat into reconstruction and rebuild their industry on principles they first glimpsed in a captured American device more than 80 years ago. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.